High-frequency welding relies on two key electrical phenomena, skin effect and proximity effect. Here we can see a schematic illustration of skin effect. Imagine an alternating current moving along a round conductor. At line frequency, or about 60 Hz, the current flows through the entire cross-section of the conductor. However, as the frequency for the alternating current increases, the current shifts to the outside edges of the conductor. At very high frequencies, the current only travels along the skin of the conductor. As the electrical reference step decreases with increasing frequency, we can observe the skin effect phenomenon. Mathematically, the electrical reference step can be written as Xi equal to the square root of the electrical resistivity of the conductor, ρ, over pi times the alternating current frequency, F, times the magnetic permeability of the conductor, mu. The proximity effect can be illustrated if we take this straight conductor and bend it into a U shape. Imagine current flowing along the conductor, down one side and back the other. When the two bends of the U are far from each other, the current flows according to the skin effect only. However, when the two sides of the U are brought closer to each other, the current begins to concentrate on the sides closest to each other. The closer these two conductors are to each other, the higher the current density on the adjacent edges. Now imagine that the conductors are not round, but they are rectangular. The same principle holds true. As the conductors are brought closer to each other, the current concentrates on the adjacent edges. If the edges are flat and parallel, the current is symmetric. But if the edges are tilted, for example in a peaked edge presentation, the current will concentrate at the corners that are closest to each other, and asymmetries appear in the current concentration at the adjacent edges. For HF welding, we do not have a U shape for our conductors. Instead, we have a V. The conductors are the strip edges, and we begin with the skin effect as the predominant phenomenon at play. As we move down along the weld V, the conductors, strip edges, get closer to each other and the current density is affected by the proximity of the opposite strip edge. Approaching the weld V apex, the current is progressively concentrated due to the proximity effect. In HF welding, frequency is a key process parameter. This is because both skin effect and proximity effect are influenced by the welding frequency. As the frequency is raised, the proximity effect is accentuated. At lower frequencies, the advantages of both skin effect and proximity effect are lost. When welding at higher frequencies, the proximity effect can be controlled in part by adjusting the weld V angle. At narrower angles, proximity effect plays a larger role along the entire length of the weld V. And at wider V angles, proximity effect is lessened, allowing frequency to drive the control of current distribution at the strip edges through skin effect. Thermatool recommends a weld V of 4 to 7 degrees for most HF welding applications. Thank you for watching this video. You can find additional educational materials related to high-frequency welding at thermatool.com.